Welcome to DP Tutorials by Donny Jarwa. In this teaching module, we will accentuate and emphasize on the expression for deriving the expression of resistivity and conductivity of a material. Now, we have also learned that when we pass potential or when potential is applied across a conductor, all these charged particles will be in the state of motion and they will be moving in one single direction. Now, in this case, we have considered this wire in the form of a cylindrical shape, and we also have been known, or let us reiterate that there will be surface these free electrons inside this conductor, and all these free electrons in this conductor will be moving in different direction, or they are in the state of random motion. That is what we have learned. Then in order to make these electrons to move in a single direction, we have to apply potential by the help of a battery. Now, when a potential is applied by the help of a battery, that means in such cases we are closing the circuit. Over here, let us place a key. That is the open circuit. That means now when we are closing the circuit, that means we insert the plug, and then this current which will flows in the circuit. The current will flows in the circuit. So let I be that current which flows in the circuit. And in such cases, this end of the conductor will be at a positive potential, and this end of conductor will be at a negative potential. All these electrons will be moving in the direction which is opposite to the field. Okay, the electric field will be in this direction. All these electrons will be drifted in this manner, and besides that, we know that since electrons are negatively charged particles, they will be attracting towards the positive end of the conductor, moving with a velocity Vd. This velocity Vd is what we define as the drift velocity. Okay, drift velocity. Now, this expression or the relation of the electric current and drift velocity is given by the relation which we have derived previously, given by I equal N E A into Vd, where N is the electron density. This N is what we define as the electron density, and that E is the charge of the electron. Is the electron density. E is the charge of the electron. E is the charge of the electron, and this E is the area of cross section. Okay, the area of cross section of that conductor. Area of cross section of the conductor. Okay, area of cross section of the conductor, or of the wire, in short, of the wire. And this Vd, this Vd is the drift velocity. The Vd is the drift velocity of those free electrons. Now we also know the expression for Vd. Okay, we know that the drift velocity Vd is given by this expression: Vd equal E, capital E, EE divided by N into tau. What is this tau? This tau is what is known as our relaxation time. Okay? Tau is what we define as the relaxation time, because each time when the electrons are moving inside the conductor, they are supposed to undergo collision. Like, for example, if this is electron number 1 and this is electron number 2 and this is electron number 3, electron 1 will collide on 2 and 2 will collide on 3. So these time taken between two successive collision is what we define as our collision time. So when we substitute on this particular equation, okay, 1 equal I equal the current I equal N E A, and then we will substitute that relation, we get E divided by m into tau. E by m into tau. And then let us simplify this relation. We will get n e square a by m into tau, okay, tau, and then we have that E, which is the expression for the electric field. But if we consider that if L is the length of the wire and A is the area of cross section and V be the potential from the battery, then we have the electric field. The expression for the electric field can be written in terms of the electric potential. The electric field E, the electric field E is V by L. The electric field E equals sign V divided by L. So when we mark this as equation number 2, it implies that equation 2 gives I equal n small e square A divided by m into tau, and the expression for E, the electric field, will be V by L. Then further from here, we can write this relation in this form. We can write m and L. This will be mL, and this will be n e square A, and that will be tau, which is the relaxation time. And over here we have this V. So this comes, if we further derive this expression, we got some value in this form. If we know that if this is your voltage, if this is the voltage, that means over here, if we cross multiply this bracket term towards the left hand side, then ml will be on the numerator term and this term will be on the denominator term. So this expression gives rise to one expression which is of the form which is similar to our Ohm's law. From Ohm's law relation, we know that V equal IR. From Ohm's law relation, it is very evident that V equal IR, where R is this resistance. R is your resistance. If you try to compare, between this equation 3 and I will mark this as equation 4, it is evident, it is very evident that from equation 3 and equation 4, it is evident that this term inside the bracket, that term inside the bracket will give us our resistance. If you compare, this bracket term will be what? Will be our resistance. This bracket term will be what? Will be our resistance. That is what we know. So from here, let us write that equation. So R, our resistance, will be equal to what? M L N E square E into tau. Also, we have the expression for resistance. We have been defined about resistivity. R equal rho L divided by A. What is this rho? This rho is what we define as our resistivity. Now, if we want to rewrite this equation, we have this term in this form. M, or I can write this as capital A, rho L by A. Then over here, this will be N E square divided by tau with the bracket. And this will be L divided by 1, L divided by A. When you look at this bracket term, and when you want to, when we are comparing this, suppose let us mark this as 5 and let us mark this as 6. When we compare equation 5 and equation 6, this bracket term is nothing but the expression for resistivity. It is the expression for resistivity. So from equation 5 and equation 6, we will get the expression for resistivity. From 5 and 6, we have from 5 and 6 we have this resistivity rho. That resistivity rho will be equal to 1 m divided by n e square into tau. So this is our expression for what? This is the expression for what we define as what? The resistivity. Okay, the resistivity. And the SI unit for resistivity is ohm meter. Okay, it is ohm meter. This is the expression for resistivity, and from here it is very pertinent. It is very pertinent and obvious that all the terms, okay, all the terms such as m, the mass, the electron density, the charge of the electron, and the relaxation time, all these are constants. Since all these terms are constant parameters, it is very clear that the resistivity of the material is also a constant parameter. That means resistivity of materials such as copper, resistivity of materials such as silver, resistivity of materials such as gold, and so, or even resistivity of materials such as alloy of the shape of manganese, okay, constantan. All those will have single value or constant value of resistivity, Then from here, that is the expression. That means this equation gives us the expression for resistivity, which means equation 4, okay, this equation number 7, I mean, this is equation 7. Equation 7 gives the expression for resistivity. Equation 7 gives the expression, okay, equation 7 gives the expression for one of resistivity, okay, of resistivity. Then when we talk about resistivity, it is purely that factor, indicating factor, which determines, which opposes the movement of charges, or which resists or stops or obstructs the movement of charges inside the conductor. Then we also know that the conductivity is another term which is the reciprocal, okay, the reciprocal of what? Of resistivity. 1 divided by rho, or reciprocal of the resistivity, is what we define as the conductivity, indicated by sigma. And the SI unit of this is what? It is Siemens. Okay, SI unit of this is Siemens, or we can write as ohm meter, okay, ohm meter inverse. That is the SI unit of sigma. Then from 7, okay, from 7 if we just take the reciprocal of equation 7, from 7 it is very obvious that sigma will be 1 divided by rho, okay, 1 divided by rho, or from here, that means this expression will be n e square into tau divided by n, which means that is this expression for conductivity. This expression for conductivity will take the form of n small e square tau divided by 1, tau divided by n. This is the expression for conductivity. This is the expression for conductivity of one of the material of the wire. Okay, so this, let us make this as equation 8. So which means that this equation 8, okay, that equation 8 gives the expression for conductivity. This is our conductivity. This is the expression for one. This is the expression for conductivity. Okay, this is the expression for conductivity. So equation number 8, okay, equation 8 gives the expression of conductivity. Equation 8, okay, gives the expression for conductivity. Equation 8 gives the expression for of conductivity. Gives the expression of conductivity. Then further, we also know about, let us derive some equation or relation between the electron mobility. Okay? Electron mobility. This is also one important character that we need to understand. Okay? Electron mobility. What is electron mobility? Electron mobility is nothing but the factor which gives us the drift velocity per unit electric field. That is our electron mobility. It gives us the indication of how electrons are moving or how the charges are moving inside the wire under the effect of the electric field. Which means that over here, this drift velocity will be given by what? This drift velocity is mu times E. That means this is the expression for drift velocity in terms of what? In terms of the electric field. First form. That means in terms of expression for this drift velocity in terms of electron mobility. Okay? Electron mobility. So this is that expression. Also, we know Vd, which we have written before, that was given by this expression, E by m into tau. This is another formula for what? This is another formula for drift velocity, but this will be in terms of what? In terms of the electric field. Okay? In terms of electric field. Okay? In terms of electric field. So these are the expressions. And also, when we have that equation, okay, when we have that equation of, okay, when we have that equation of Vd, okay, when we have that equation of Vd equal E tau divided by m, okay, when we have the expression of Vd equal E tau divided by m, okay, let us rewrite that equation. Vd equal E, okay, E by m into tau. By definition, mu is equal to Vd divided by E, which implies that this Vd, if we cross multiply this E towards this side, then we get Vd divided by E, and we are left with this expression Em, E tau divided by m. And what is this expression? This is the expression for mobility. Mobility will be equal to what? E by m into tau. Okay? E by m into tau. E by m into tau. This will be one form of expression for electron mobility from the definition itself, and this will be another form of the expression for electron mobility in terms of the relaxation time. Okay? In terms, this will be in what? In terms of relaxation time. Okay? In terms of relaxation time. In terms of relaxation time. In terms of relaxation time. So remember, these equations are very, very important. This is the first form of Vd in terms of electron mobility mu. This is this expression for Vd in terms of relaxation time. Expression for Vd in terms of drift velocity and electric field. And expression for Vd in terms of the relaxation time. So these are some of the key features that we need to know. Also remember that we need to stress upon the SI unit, okay? SI unit of electron mobility. The SI unit of electron mobility, from the definition itself, it is Vd divided by E, which means that it is meter per second velocity. And for electric field, we know that electric field will take the form of V divided by L, okay, V divided by L, which is what? Which is volt, okay, meter inverse. So from here, that means this will be volt meter inverse. So if you try to solve this one, that means meter inverse and meter will give us what? Will give us meter square. Okay, this will be meter square, then volt inverse, second inverse. This is the unit of what? This is the unit of electron mobility. So just go through those derivations so that you will understand all these important formulas which are important from examination point of view to do some relevant derivation. Thank you.